Hi everyone. So let's talk a little bit more about diagonalization. So first of all, remember that to diagonalize an n by n matrix, you need n linearly independent eigenvectors for that matrix. Those vectors will form the columns of the matrix P that you'll use to diagonalize. So one of the things that could be difficult here is you could go through the process of finding eigenvalues and eigenvectors, but then how do you know that those eigenvectors that you get are linearly independent? In the 2 by 2 case, it's not that big of a deal. You can just sort of look at two vectors and say that they're linearly independent because they're not multiples of each other. But in higher dimensions, it's not so easy to just look at the vectors and see that they're linearly independent. So here's a useful fact that helps with this. It says that a set of eigenvectors with different eigenvalues is always linearly independent. So here's an example that would make use of this fact. Here's a 3 by 3 matrix, and the question is it diagonalizable? And the answer is yes. And what's cool is that you can actually figure that out without doing any calculations at all. So there's a couple of things that come into this. So the first thing is that for an upper or a lower triangular matrix, the eigenvalues are just the entries along the diagonal. And this comes from the fact that the determinant of an upper or lower triangular matrix is just the product of the diagonal entries. And to calculate the eigenvalues, you calculate the determinant of a minus lambda I, which will be upper or lower triangular. And so you'll be multiplying the diagonal entries of a minus lambda I. And that's just going to be factors. In this case, it would be 3 minus lambda times 4 minus lambda times 2 minus lambda. And so that means that when you calculate the characteristic polynomial that way, you get it in a form that's already factored, where the roots are the diagonal entries of A. So anyway, with this matrix A, we don't need to do any calculations to see that the eigenvalues are 3, 4, and 2. So then the next thing is that for each eigenvalue, there is at least one eigenvector, because that's what makes them eigenvalues in the first place. And so then, because there are 3 different eigenvalues, we can get one eigenvector for each of those eigenvalues, and this useful fact tells us that those will automatically be linearly independent, and so then we'll have a basis of eigenvectors. And so the conclusion is that A is diagonalizable. Now, if you actually wanted to diagonalize A, as in find that matrix P such that P inverse AP is equal to D, then you would have to go through the work of finding the eigenvectors, which is a little bit of calculation, but it's not too bad. But if you just want to say whether or not A is diagonalizable, you can answer that question without doing any calculations whatsoever, and the answer is yes. All right, so let me show you a proof of this useful fact. It involves a little bit of a trick, but it's a good trick for you to see. And I'll do it just in the n equals 2 case, but this case already contains the key step. The general proof is an induction proof, and this case already contains that key step that you would use to make the induction. Okay, so let's suppose that v1 and v2 are eigenvectors of A with distinct eigenvalues lambda 1, lambda 2. And then we want to prove that these vectors are linearly independent, which means we need to show that the only solution to the equation c1v1 plus c2v2 equals 0 is the trivial one where c1 is 0 and c2 is 0. So let's start with this equation, and we'll try to manipulate it so that we can solve it. So one thing we can do is we can multiply both sides of the equation by lambda 1. You might wonder why, but hey, that's why I said this was a trick. We do some stuff that seems kind of weird, you don't know why we're doing it, and then all of a sudden everything works out. So another thing we can do is we can multiply both sides by A. And then here we can distribute the A and pull out the scalars. And then we can use the fact that v1 and v2 are eigenvectors. So A times v1 is lambda 1 times v1, and A times v2 is lambda 2 times v2. Okay, so now let's call the equation on the left equation 1, and the equation on the right equation 2. And let's subtract equation 2 from equation 1. And you'll notice that when you do that, the first term will cancel. The lambda 1 c1 v1 is in both of those, and they cancel. And then the other terms, they both have c2 v2, but one equation has a lambda 1, and the other equation has a lambda 2. And so when you subtract the equations, what you get is lambda 1 minus lambda 2 times c2 v2 equals 0. Now what do we know about what's here in this equation? Well, we know that v2 is an eigenvector, And being an eigenvector, it has to be a non-zero vector. So v2 is not 0. So how can you get 0 when you multiply v2 by some scalars? The only way that can happen is if these scalars are equal to 0. But we've assumed that lambda 1 and lambda 2 are distinct, and that means that lambda 1 minus lambda 2 has to be non-zero. And so the only remaining possibility is that C2 is 0. And then once we know that C2 is 0, then we can plug that back into the original equation, C1v1 plus C2v2 equals 0, and we get that C1v1 has to be 0. And now it's a similar argument. We know that v1 is an eigenvector, so it has to be a non-zero vector, and the only way you can get 0 in this case is if C1 is 0. And then there you go. We've proven that the only possibility is that C1 is 0 and C2 is 0. So this fact is really useful because it means that if you have n distinct eigenvalues of your n by n matrix, then it's automatically going to be diagonalizable. But I want to show you an example of a matrix that doesn't have n distinct eigenvalues, but is still diagonalizable, because that can happen. Okay, so here's the example. Is this matrix diagonalizable? Well, the first thing you'd want to do is calculate the eigenvalues. So here is a minus lambda I, and because you've got those zeros, it's convenient to do a cofactor expansion across the bottom row or the last column. And actually, either way, you end up with the same thing. And that is that the determinant of a minus lambda I is 5 minus lambda times the determinant of this 2 by 2 matrix. And the determinant of that 2 by 2 matrix is 1 minus lambda times 2 minus lambda minus 12. And when you simplify the expression inside the bracket, you get lambda squared minus 3 lambda minus 10. And you can factor that as lambda minus 5 times lambda plus 2. And so now we can see what the roots are. There's lambda equals 5, and lambda equals minus 2. And because 5 appears twice, we're not in that situation that we were discussing earlier, where we have distinct eigenvalues. So at this point, you should be concerned. It's possible that the matrix is not diagonalizable. But to know for sure, you need to actually look at the eigenvectors. So let's see what happens when you put in lambda equals 5. So then here is a minus 5i, and if you put this into reduced echelon form, you get this. And this is good news because there are going to be two free variables, and that means that you'll get two linearly independent eigenvectors for lambda equals 5. And that's actually going to be the thing that makes all the difference. I'll go through the remaining details, but at this point you really can say that, yeah, it's going to be diagonalizable. Okay, so here you have the one equation, x1 minus 3/4 x2 equals 0, with x2 and x3 both being free. So then that means that x1 is 3/4 x2. And so as a vector, the solution is 3/4 x2, x2, x3. And you can split that up into an x2 part and an x3 part, which gives you your two linearly independent eigenvectors. And maybe this is a good place to point out that you can rescale these eigenvectors, because you'll still have eigenvectors when you rescale them. And if I don't want that fraction, that 3/4, I can just multiply that vector by 4, and it'll still be just as good of an eigenvector as before. So the eigenvectors we get are 3, 4, 0, and 0, 0, 1. And then to get a third linearly independent eigenvector, we would look at the other eigenvalue, lambda equals minus 2. I'll do this part a little more quickly. Because you're subtracting minus 2 times I, it becomes a plus 2i, and so this is what you get. And then you put that into reduced echelon form. And so the equations that come from that are x1 plus x2 equals 0, x3 equals 0, and x2 is a free variable. And so as a vector, the solution is minus x2, x2, 0. You pull the x2 out, and you get the eigenvector minus 1, 1, 0. And now here, that useful fact can come into play. This eigenvector will automatically be linearly independent with the other two eigenvectors because they come from different eigenvalues. And so that means that we have in fact found 3 linearly independent eigenvectors, which means that A is diagonalizable. And we could in fact use these 3 eigenvectors as the columns for the matrix P that would diagonalize the matrix. All right, well, there are a lot more things. There are questions about what you do when there are complex eigenvalues, There are questions about what other things you can do when the matrix isn't diagonalizable, but unfortunately we're not going to have time for those things. So for our purposes, this is good enough. All right.